Welcome to YouTube video lecture 16. In the last lecture we have seen permutation group. When we call a permutation odd and even, and the group of even permutations, that is alternating group. In this lecture we are going to begin with conjugates. So when we say an element is conjugate to another element of group, so let us begin with the definition. Right, so we define let G be a group and AB belongs to G. So we start with two elements and we say that B is a conjugate of A. So we say that it's just like similar matrices. So we say that B is a conjugate of A. If there exists some C, so if there is some C in G, so if there is an element in G such that we can write B equals to C inverse AC, such that B equals to C inverse AC, right? And in this case we write so in this case we write A is similar to B, or A is conjugate of B. This is A is conjugate of B, or better we should denote this as B is conjugate of, or that is A is similar to B, or A is equivalent to B. Okay, so two elements, they are said to be, so one B is said to be conjugate of A if there is some C such that B equals to C inverse AC. So let us consider some example. Of course, every element is conjugate of itself. So it's not that there are no conjugates. You can always write A equals to E inverse A E. Right? This is always there. So that is A is, or in other words, A is a conjugate of A. A is conjugate of itself. So it is there. So B is conjugate of A. Oh, sorry. B is a conjugate of A if B equals to C inverse AC for some C. So A is always conjugate of itself. But are there any other conjugates? If you can observe this, if the group is abelian, wherever we have this C inverse AC, whenever the group is abelian, this is going to commute. AC is going to be CA, C inverse is identity, so it is going to be A. So in abelian group, only conjugate, if B is conjugate of A, then B is equals to A. This is what we are going to get, right? So we can state this as a remark: A is conjugate of A, and if the group is abelian, if G is abelian and B is conjugate of A, then what is B? B equals to C inverse AC for some C in G, but this is equals to C inverse CA, then it is equals to A. So that is B equals to A. So in an abelian group, in any abelian group, so in abelian group this is not interesting. In any abelian group, the conjugate of an element is the only conjugate of an element is itself. એના સિવાય બીજો કોઈ મળે નહીં. In an abelian group, the only The only conjugate of an element is itself, right? So we need to consider examples in a non-abelian group, and the non-abelian group which we have seen is S3, standard non-abelian groups, the smallest one, the first one, right? So we'll consider that examples later on, but what you see this notation, we have a notation. So what does this mean? This means that this A is conjugate, that we have seen one, that A is B is conjugate of A is similar to B. That is the kind of notation we are writing. And another thing, that every element is conjugate of itself. So A is conjugate of A. So what we are going to get to this is, yes, your guess is correct, that we are going to show that this is an equivalence relation. We are relating two elements of a group. When these two elements are said to be related to each other, if B is a conjugate of A, then we say that A is related to B, or A, this tilde B, A sim B. That is a symbol which we use. Right? So next lemma. Conjugacy or this relation, that is being conjugate of, is an equivalence relation. Right? So conjugacy is an equivalence relation. That is what we have to prove. Reflexive already we have stated in a lemma, but we can also consider like this: A equals to A inverse AA. Here we have considered A equals to E inverse AE. E inverse AE. So B should be written as this C inverse AC. But here A equals to E inverse AE. That means A is conjugate of A. Other way of writing A is a conjugate of A is this: A equals to A inverse A. So then, right, so that is, this means that the relation reflexive. Now we prove symmetry. So the second property, what we are given is, so this is given. Suppose A is related to B. So then that is, this implies B equals to some x inverse AX for some x in G, right? So B equals to x inverse AX for some x in G. Then we have to show that A equals to some element inverse. So what we have to show? We have to show that A equals to some y inverse by. So how do we show this? Then we have B is related to A. So then yes, multiply by x on both sides. So this implies x b x inverse equals to A. Right? So multiply to the left by x. So we have xb equals to ax, and multiply to the right by x inverse on both sides. So we have xb x inverse equals to A. But then this we can write as x inverse inverse. X we can write as x inverse inverse, and then b, and then x inverse equals to A. So that is y inverse b y equals to A. We do not write this much. If it is understood, then it is fine. So where y equals to x inverse. So remember that it should be not x a x inverse, it should be x inverse a x. So that means here x was there, but we wanted to write as an inverse of some element. So that is x inverse inverse b x inverse. So x inverse is the element y which will work for us, and this implies b is related to a. So hence the relation is symmetric. So thus this is sorry symmetric. Now finally transitivity. So we are given a is related to b, and b is related to a. B is related to c. Right, this is what we are given, and so that means that is b equals to, we can write x inverse ax, and c equals to, we can write y inverse b y inverse by for some x and y in G. For some x and y in G. Yes. Right. Then we have to, what we have to show here. So let us write here what we have to show. We have to show that A is related to C. A is related to B related to C, then A is related to C. So therefore that we have to show that C equals to Z inverse AZ for some Z in G. So we have to find such a Z that this can be written. So how do we write? So we have to start with C. So we start with C. So now C equals to, but what is given? It is given y inverse by. So we start from C and we have to bring A into the picture. So then B is also, from B we can use this to bring A into the picture. So we have y inverse, and B we can write as x inverse A x and then y. So we have y inverse x inverse, but y inverse x inverse, so these two can be written as, I am writing directly, I can write this as xy inverse A and then xy. Is it clear? So this y inverse x inverse I have written like this, xy inverse, and then here this xy is this. So that is our z. So this we can write as z inverse A z, where z equals to, because G is a group, then xy inverse xy is an element of where z equals to xy, and this is an element of G because G is a group, right? So then that is there's A related to C, and hence, and so this is transitive. So we have transitivity is also verified, hence this is an equivalence relation, hence conjugacy is an equivalence relation. So this means A C is conjugate of A. Okay. So that means if B is conjugate of A, and this means C is conjugate of B, then C is conjugate of A. Right, so we have verified that it's equivalence relation. What comes next? After equals, whenever we have a relation, whatever comes next is the equivalence class, whenever we have an equivalence relation. So we denote this equivalence class by CA, equivalence class of A. So denote the equivalence class of A in G by capital C of A. So equivalence class we denote by C of A. What is C of A? So C of A, then C of A is set of all those elements which are conjugate of so set of all elements X in G such that X is conjugate of A. X is a conjugate of A, and that means X in G such that X is a conjugate of A, we denote by this. And then what we know, what is this relation? X belongs to G such that X equals to Y inverse AY, like this, Y inverse AY for some Y belongs to G. So then if X is this, then why do we keep X? We can directly write that this is a set of all Y inverse AY such that Y belongs to G. So these are all conjugates. Or we can also write or X inverse, if you don't want to use this symbol Y, then you can write X inverse AX such that X belongs to G. Now this X is not same as this X, but just instead of Y I am writing X, right? So this is the set, this is CA. So CA is a set of, so this is called conjugate class of A. CA is called, so for this, so C of A is called conjugate class of A. Right, so this is definition of conjugate class of A, the set of all conjugates of A. So this is Y inverse AY, so that is the set of all conjugates of A. Set of all conjugates of A. Right, so we have denoted by CA the conjugate class of A. Of course, this is non-empty. A is always in the class. A is a conjugate of itself, as we have seen in the reflexivity. And we denote this the number of elements by small ca. So by ca, c suffix a, we mean the number of elements. So by this we mean the number of elements in CA. So that is, the CA is nothing but it is the cardinality. This is the notation which we use for cardinality. C of A, this is the cardinality of C suffix A is cardinality of C of A, CA, or which is also we write sometimes like this, right? Okay, so now let us observe how many elements will be there in CA. That is our next target. What is the relation? Do we get any other elements other than the element itself? As we said that in abelian group, in the remark we have seen. So here, as we have seen, that if G is abelian, then the only conjugate of an element is itself. So only one conjugate, because you can see this commutes A and C. So we will get only A. So in that case, we do not get any other element. Suppose the group is non-abelian. It is always possible to find a non-trivial conjugate. I mean, other than itself. Is it always possible to find a conjugate? That is the question. Right. So you get the question that if the group is non-abelian, and if we pick any A in G, G is non-abelian, is it always possible to find other conjugate other than A? Is it always possible? So, as you can observe, that we don't need the group to be abelian. In the worst case, what can happen is that this C can commute with A. Then A will not have any other conjugate. I am again repeating, group may be non-abelian, but suppose all the elements commute with A, तो ऐसा कोई C मिलेगा ही नहीं, such that C inverse AC is not equals to A. If all the other elements of the group commutes with A, then B equals to A. ग्रुप चाहे नॉन अबिलियन हो, लेकिन फॉर एग्जांपल आइडेंटिटी, आइडेंटिटी का क्या कॉन्जुगेट होगा? इफ आई वांट टू राइट द कॉन्जुगेट ऑफ आइडेंटिटी, E equals to C inverse E C, but this will commute anyway, so this is anything anyway, this is C itself, but actually this EC equal to CE, so this is nothing but identity. So identity has no other conjugate except identity. So if we can find some element A for which all other elements commute, then you take any C inverse AC, it is going to be A, even if the group is non-abelian. बीजा कोई element, there may be some elements xy not equals to yx, but for A, xa equals to ax, for A, ya equals to ay. Suppose it happens for every element, then it is not going to give any other element other than A itself. So we don't, of course, when the group is abelian, there is only one conjugate of A, that is A itself. But in the worst case, I mean, in other cases also, it can happen that A has only one conjugate, and that is itself. In cases like where every other elements commute with A. So that means this set is important. Which set? The set where every elements commute with A. It's important to understand the number of conjugates or the conjugates of A. So this set. Before I give definition of this set, we should also note what happens because of this this conjugate class. So we can count the number of elements in the group by these classes. If I want to count the number of elements in the department in semester 1 and semester 3, then there are 4 classes. Now semester 1 has not begun, but usually there are 4 classes. Semester 1 2 classes, semester 3 2 classes. So there are 4 classes. So how do I count the elements? Equivalence classes. So there are 4 classes. So I pick one element, so one student from each class, and I ask him or her how many students are there in her class or his class. Then I add those 4 numbers. I do not need to count each and every one of the student. How many students are there? I don't need to count each and every one. I don't need to list each and every one of them. I can just take 4 representatives, any 4 students from, but from distinct class. એક જ ક્લાસમાંથી 2 જણા લઈશ ને તો there will be problem. If I take 2 students from single class, then there is a problem. Then I cannot get the exact number. So I should take one student from each class. So CR from each class, and then I ask CR, or any the CR is not present, I can call anybody. So one element, one person I need from each class. Then I'll ask them how many students are there in their class, and those total I get. Then I get the total of students of our department. So that means the in the same way, G is also divided in this class. So how many elements are there in G? So then summing up, we can say that so suppose G is a finite group. So if G is finite, then what is order of G? Order of G will be, order of G will be summation CA. Right? What is CA? Summation CA, that is nothing but this is, I can also write this as summation CA. Cardinality of CA here. Yes, so this summation cardinality of CA, which is be denoted by small ca, C suffix A. But we should not take the sum. What is the sum over? It is not for all A in G. If I take for all A in G, then there is a big problem. If I ask every student how many students are there in their class and I add them, then there is a problem. I should take 4 representative from all 4 classes. So I should, that means where the sum is taken over, where the sum runs over or the sum is taken over, કેટલા એલિમેન્ટ્સમાંથી સમ લેવાનું? It is taken over exactly one representative It is taken over exactly one representative, exactly one A from each conjugate class of G. Right, so sum is taken over one A from each conjugate class of G. So this is one important observation that so this will be useful uh, in further. Every time we'll be using this. So let me mark this by some box. Yes. So we have such an expression for order of G. If G is finite, even if G is not finite, the number of elements can be uh, enumerated like this. But if G is finite, then order of G is exactly this elements in each class, because now G is divided into each class. So is it clear? If it is not clear, just go back if you need to revision. That is the advantage of this video, that you can just go back and uh, revise all this what we have seen. In the class I usually go back and revise, but I don't want to make this video longer and longer because my videos are getting longer, past two videos. So as I said, again I am repeating at least this much I want to repeat because it is going to come next. So abelian group, no conjugate of A other than A, because the C inverse AC will be going to be A itself. Non-abelian group, what is the chance of getting a conjugate? How many different conjugates will be there? But you see, if it is non-abelian group, some elements may not commute, but there are elements which can commute with other elements. So for example, every element commutes with identity, so conjugate of identity is itself. And suppose every element commutes with A, every C in G commutes with A, then C inverse AC is going to be A itself. So we are not going to get any other conjugate of A other than A. Yes. So that means the set of all those elements which commute with A is important to us. If that set is whole group G, every elements commute with A, then there is no other conjugate. So this is the definition we are writing, that is called the normalizer of A. So that is the definition. Let me write here. So let G be a group and A belongs to G. Oh, this is a box. Okay. Let G be a group and suppose A is in G. Then the normalizer of A right? So this is called normalizer of A. Is denoted by NA. It is sometimes also called the centralizer of A, but we are using the word normalizer of A. Is denoted by NA, and it is defined as or it is the set. You can say that NA equals to set of all x in G, set that AX equals to XA. Set of all x in G, set that AX equals to XA. That means set of all those elements of group which commute with A. A is fixed. See, A is fixed, that is why we are writing here A. Right? A is fixed, so set of X is changing. Set of all those elements which commute with A. A ની સાથે જે commute કરતા હોય ને એવા જ elements લેવાના. So we are not saying any B other than this A. So A is fixed. Elements keep on changing. Check that they commute with A. Then it is there in the normalizer. If it doesn't commute, then it is not in the normalizer of A. For every element, we have NA. For every element A in G, we have NA. So this depends. So this is a definition of that is called normalizer of A. In abelian group, what happens? In abelian group, what happens to the normalizer? Normalizer is going to be the group itself. because every element commute with every other element. So if the G is abelian, sorry, I have taken a highlighter. Note that if G is abelian, then Na equals to G. Group is abelian, then every element commutes with every other element. So A સાથે તો બધા commute કરવાના જ. Not only that, if A belongs to Z, that is also we sometimes write ZG. A is in the center. Center means what? A commutes with all elements of G. Then A commutes with all elements of G. A commutes with all, by definition. This is by definition. A commutes with all the elements of G. So in this case also, if A commutes with all the elements, Ax equals to XA. So બધા X આમાં આવશે. So every X is there in Na. So in this case also, we can say that Na equals to G. So we have two cases, right? So this is one. In other cases, this may be a proper subgroup, which is interesting. So now the thing is, in other words, we can write, in other words, Na is the set of elements all elements of G that commute with A. Right. So now one exercise I leave for you, or maybe I can show that Na is a subgroup of G. So let G be a group. Let me do it. Let G be a group and A belongs to G. Then Na is a subgroup of G. It's very simple exercise. What I suggest is you stop the video, you try to do it, and then see if you can do it or not, what difficulty you have, because you should be able to do it by now, all such easy exercises. But let me do it here itself for you, so you can verify. So two things we have to show is, say Na is closed under the product of G, and every element in Na has an inverse. So the first thing we start, let X and Y belong to n of A. Then we have to show that X into Y, so X product Y, whatever the binary operation is there in G, so X, that product XY is in Na. So X and Y in Na, so then this means what? XA equals to AX and YA equals to AY. So if I take two elements in Na, that means X and Y are in Na, that means X commutes with A, that means XA equals to AX. Also Y is in Na, so Y commutes with A, so AY equals to YA. Now what we have to show, XY is in Na. To show that XY is in Na, n of A, so normalizer of A, XY, that means XY should commute with A. So XYA should be equals to A XY. What we should have? So we should have XYA, and somewhere we should have this equals to A XY. If we show like this, XYA equals to AXY, that means XY commutes with A. So then we are done. We have shown that it is closed under the product of G. So but by associativity, we can write this as By associativity property, we can write this as x, y, a. Now, y is in NA, so ya equals to ay. So that already we have, so we can write this as ay. The reason already we have here ya equals to ay. So since y belongs to NA, ya equals to ay. And then we can again use associativity. Very simple. This we can write pair up x and a first. So associativity, and then xa equals to ax. Reason is since x belongs to NA, x commutes with a. So xa equals to ax. So this is also we have done xa. So we have already x belongs to NA. So we have axa equals to ax. Right. So this also. So that means, and then again associativity. By associativity, we can write this. So that means xy commutes with a. Right. So xy commutes with a. Therefore, xy belongs to NA. So NA is closed under the product of G. Now the second thing, we have to show that every element in NA has an inverse. So let Ax belongs to normalizer of A. Then what we can say, then again, uh, as we have done above, xa equals to Ax. That means Ax commutes with A. Now we have to show that X inverse also commutes with A. But from this, xa equals to Ax, what do we have? So take X inverse. So multiply by X inverse on both sides. So we have A equals to X inverse Ax. Then multiply by X inverse on the right side. So we have Ax inverse equals to X inverse A. And then we are done. Ax inverse equals to X inverse A. That means X inverse commutes with A. So X inverse is in the normalizer of A. So every element has an inverse. So hence an A is a group. Is a subgroup of G. Right. So Na is a subgroup of G. I hope, yeah, this is the statement I have written. Na is a group. In fact, it's subgroup of G. So now we go to the relation between Na and C of A. As we have seen that there is some relation. Why this came into picture? It's not that one by one we are going to define something to call a unit. It is because we are interested in what are the conjugates of A, and the conjugates of A other than A is possible only if we can find some element which does not commute with A. So if all the elements commute with A, then no other conjugate, as I said, even if the group is non-abelian. But if all elements commute with this particular A, then A will not have a conjugate. So that is why the elements which commute with A is important. That is why this NA normalizer is the set, which is nothing but precisely the set of all those elements which commute with A. So that came into picture. What we have observed, normalizer is a group. The question is whether conjugate set of all conjugates is a group or not. That is, I ask you to check. Yes, and now the relation between normalizer and the conjugates. Right. So let me recall what does a conjugate of A look like. So conjugate of A, we have seen it is y inverse A y. So this is a conjugate of A, where y belongs to G. So suppose no elements of G commute, no element commutes with A. तो कितना conjugate मिलसे? A के साथ अगर कोई एलिमेंट कम्यूट नहीं करता, then how many conjugates we get? We get different, possibly different. We don't know whether they are distinct or not. So how many, at most, how many conjugates we get? How many conjugates we get? Order of G. Change करते जाओ ना. This is a conjugate. This is a conjugate. C inverse AC. So for every element in G, you can make an in the conjugate. So maximum, how many conjugates will be there? Maximum, it is order of G. Agreed? How suppose G has 5 elements, then x inverse x inverse AX is a conjugate, y inverse AY is a conjugate, C inverse AC is a conjugate, Z inverse AZ is a conjugate, E inverse A. So 5 elements. So one will be A also. So let me not go, but how many elements maximum will be there? Maximum order of G. But when they are going to be the same element, for example, here we are going to the same element as I was saying. A inverse A is also conjugate of A, which is nothing but A itself. So it is A is the conjugate. E inverse E inverse AE, that is also A. So here these two elements E and A gave us the same conjugate, right? Here they are giving the same conjugate. So what is the guarantee that this is a conjugate, this is a conjugate, but what if we hit upon the same element? So how many distinct conjugates will be there? So that means if all are distinct, then we get maximum order of G. But when do we don't get distinct? If this guy commutes. So that means it should be related. Not only that, so the relation between the number of conjugates and the normalizer of A in G. So that is the next result which we are going to discuss. So the relation is this. And this is an important result. So let G be a group and A belongs to G. Then the number of conjugates of A. What is the number of conjugates of A? This is the set of all conjugates of A. But its number we are denoted by C of A, small c of A, if you remember. Then C of A is nothing but it is index of NA in G. And if G is a finite, so be a group. Let me consider G is be a finite group. So this is a finite group. Then we can write index of H in G is order of G upon order of H. So index of NA in G is order of G upon order of N of A. Right. So it is then nothing but the number of distinct conjugates of A is nothing but the number of distinct right or left cosets of NA in G. Right. So that is the proof. Now, so when we want to show that two sets have the same number of elements, what we do is we give a one-one correspondence between them. What is one-one correspondence? It's a one-one and onto function between them. So consider the set G quotient NA. Oh, for this N here must have to be a normal subgroup. So this is NAX. So check whether it is a normal subgroup or not. NAX for such that X belongs to G. So NAX HX. So the set of all right cosets of NA in G. Right, and now we define the relation. So define a function, not relation, define a function phi. Define function phi from this G quotient NA to CA. Right, G quotient NA to C of A. So every right coset, you define a conjugate. And if you show that this function is well defined, 1, 1 and O2, then we are done. That means every right coset there is a conjugate, every conjugate there is a right coset. Number of they are same number. So that means what is the number of distinct right coset? Order G upon order of N when G is a finite group. So how do we define? By. So give me a right coset here. We have to take a right coset here. So that means I must take some NAX, right? So this is a right coset. As soon as I take a right coset, I get some X. And how do I define conjugate of A? Using this X. Yes, so that means X inverse AX. This is a natural way. We don't have to think also. We don't have to remember this kind of proofs. Why? Because when we want to show that these two sets have same number of elements, what is order of G upon order NA? That is nothing but the number of distinct right cosets of NA in G. So take G quotient NA naturally. That is what we want to show, that it is exactly the number of conjugates of A. Number of conjugates of A. That means we have to take the map from G quotient NA to CA. So if I define like this, NAX for a right coset. As soon as I take a right coset of NA in G, I'm getting an element of G X. So I take X inverse AX, that is nothing but the conjugate. So I want a conjugate, so that is the natural way to define. Now we show that this function is well defined and 1 1. So we show that phi is well defined, and right now let us say 1 1. I was going to write bijective, but let us say 1 1. So how do we show it's well defined? So if we have two same right cosets, the image also should be same. Is it clear? So suppose we have two right cosets. So for NAX, so for NAX and NAY in G, for NAX and NAY in G, suppose they are equal, NAX equals to NAY. So this implies that you can write this, multiply by X inverse both sides. So we have NA E, which is nothing but NA on the left side, and on the right side Y X inverse, X inverse, which was NE, and so this means what? So this means Y X inverse belongs to NA, because when we have H equals to HX, how carry if and only if we know that this X belongs to H. This happens. So by this we can say that, let me remove this, I don't want this to be in notes. Yeah, so that means when NA YX inverse equals to NA, so that means YX inverse is in NA. But this implies what? NA ની અંદર ક્યારે આવે element? If it commutes with A. So YX inverse commutes with A. That is, so YX inverse A equals to A YX inverse. Okay, all this is okay, but where are we going? આપણે શું prove કરવું છે? Oh, we have to show that we have started with the element is same, then image also must be same. The image of NAX is X inverse AX. We have to show that it is same as Y inverse AY. So then this is multiplied by Y inverse on left. So we are left with XA, and here Y inverse A Y X inverse. Multiply by X inverse on right. So we have X on the right. So XA X inverse AX equals to Y inverse AY. And we are done. So the image of which means that phi of NAX equals to phi of NAY. Right? So elements are same, the image is same. So this is well definedness. What about 1 1? Go back the same way. So this is same, this is same. Right? So this phi, which is 1 1, which is well defined, you should be clear. Right? This way we are going. We have done what is well defined. Now going back is 1 1. So thus phi is well defined and 1 1. Well defined was this side, and 1 1. 1 1 was the reverse implications. So now we show that phi is onto. So now we show that phi is onto. How do we show onto? So so for onto we have to take an element here, and then we have to find an element which is mapped to this by phi. So start with an element in CA. So conjugate of A. So as soon as you pick a conjugate of A, you are through. This onto is very clear. So let y belongs to CA, but conjugate of A, what does it look like? So then y equals to x inverse AX for some x in G. Now as soon as you take x, we are done. X molecule, so we can get a right coset of Na so with respect to x. So NaX, so take that. So then NaX is a right coset of so it is in of Na in G, so it is in G quotient Na. Not only that, and what is phi of NaX? Phi of NaX equals to x inverse AX, which is the element we started with. This is y. Y is start. We have found an element in the domain, which is so thus hence phi is onto. Hence phi is onto. So it is 1 1 and onto, and therefore thus phi is a 1 1 correspondence. It's a well-defined function which is a 1 1 1 to 1 correspondence. 1 1 to 1 correspondence means 1 1 and onto function. So phi is a 1 1 correspondence between G quotient Na and Ca. So the number of elements in this, which is this, so the number of elements in both are same. So C of A, the cardinality, which is small ca, is same as index of, so order of this is nothing but index of Na in G, which is nothing but order of G upon order of N of A. Right, so this is important. And now we see that equivalence class has divided. So how do we count the elements of G? This we have seen the box I have made, right? Order of G is what? Sum over the Ca, where the sum is taken over exactly one A from each conjugate class of G. And now this Ca we have found. What is this Ca? This is Ca is nothing but order of G upon order of Na. So hence I can write this as, so as a corollary, what I have, for a finite group G, for a finite group G, what is order of G? Order of G equals to summation Ca, but now the Ca I can replace by summation order of G upon order of Na, and this is called the class equation of G. Right? This is called the class equation of G. But where what about this sum? Sum is taken over. So where the sum is taken over, where the sum runs over 1A from sum runs over 1A, one element A from this A is element, one element A from each conjugate, or 1A in each O, 1A in each conjugate class of Chokma Unathat, each conjugate class of G. Right? So the proof is simple. What we know is is a corollary. So we know that WKT order of G is nothing but summation Ca, and this is or Ca is nothing, just we have proved that is order of G upon order of Na. So where the sum runs over this each conjugate class of this. Okay, so this equation is called, so let me put a star over here, and then I write what is this star. So this equation is star. is called the class equation. Yeah, so that is called the class equation of G, which is very, very important for problem solving. Also, we are going to use this so many times. Otherwise, also is important. So this is called the class equation of G. Right? We are going to see further another version of this class equation from this itself, but that is going to be in the next video. So let us see one example. Let us consider example of S3. So we have done so much theory part. Now what about NA and CA? But example based on this. So consider G equals to S3. Of course, we are taking S3 because we know abelian group. None of this makes much interest. It's not interesting. So in abelian group, it is not. We are not going to get any other conjugate other than itself, the element. So we take S3, and now we compute all. So compute NA and CA. CA for all S in, for all A in S3. Right. So let me do a couple of them, and then you can do the rest of the others. So let us take A equals to E. So A is identity, and now what about NE? What are the elements that commute with E? So NE is going to be the whole set, right? So since every element commutes with E, we have N of E equals to S3. It's the entire set. It's the entire group. So E also commutes with this E phi psi psi square phi psi and psi phi, which is phi psi square. Right. So this is S3. What should be CE? CE is what? Yeah, actually, see, if NE is entire set, then what? How many conjugates we should get from this? The number of conjugates is so. This is also an important result we should observe. Number of conjugates is order of G upon order of NA. So there also we can verify the number. So NA is whole group, then order of G upon order of NA is 1. So we should be getting only one conjugate here. So let us check that. So if I want to compute CE, so I need to compute what are the elements. So how many elements commute with E? How many elements different conjugates of E? So E inverse E, which is E. Then we have phi inverse E phi. This is again E, right? Because every element commutes with A, so we are going to get E. So this is nothing but singleton E. Is it clear? So psi inverse, this is also a conjugate of E, psi inverse E psi. But because it is going to be E itself, so for all these elements is E. So here it is 6, here it is 1. So A equals to E, which is very clear. So not much thing to do. Now let me consider A equals to uh, phi, second element, A equals to phi. And we compute n phi. So how many elements commute with phi? So that will give us n phi. So let me write. So E phi equals to phi E. So n phi identity to outside n A is a subgroup. So a subgroup is there. So identity is always there. Now what about phi? Phi equals to phi square, and they commute. So phi. So this interchange. So they can commute, right? So phi is also there. Every element commutes with itself. So this is also there. So the two elements are always there. If the element is other than identity. And what about psi? So psi phi equals to is it same as psi phi is same as phi psi square, but phi psi square. So this is not same as phi psi. psi phi and phi psi, they do not commute, so a nahi aave. Phi psi we cannot write here, so it is not there. What about psi square phi? Psi square phi is phi psi, which is not phi psi square. So psi square also does not commute. Psi square phi is not equals to phi psi square. That means psi square also does not commute with this. So psi square nahi aave. So what will be the next thing? What about phi psi? Phi psi. So that on the one side we have phi psi, phi psi phi. Is it equals to phi psi? But what about this? This is same as phi square. Phi square is identity, so this is same as psi. But on this side you have psi phi. Psi phi is same as phi psi. Phi 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 mali jase na. So let me write this. So this is same as phi and phi psi. So and this is going to be phi psi square. So this is going to be psi square, which is not equals to psi. So again, that is not going to commute. Similarly, you can check that psi phi and phi. Psi phi also does not commute with phi. So this is only two elements. N phi is only two elements. So n phi we have computed. Only two elements commute with phi. One is identity, another is phi. No other element of this. Other four elements don't commute with phi. So there are only two elements. So what should we expect? So by the above theorem, what do we know? We know that Ca equals to order of G upon order of Na. So this implies C of phi, the cardinality of C of phi is equals to, so this is cardinality of C, capital C of A. So cardinality of C of phi equals to order of S3 upon order of N of phi. Order of N of phi. So which is 6 upon N of phi. We have found two elements here. So this is going to be 3. So there are three conjugates of phi which we know. We have to find what are those three. So there will be 3. So this is verification also, so that we don't make mistake. Now what are the conjugates of phi? Let me write the conjugates of phi. Conjugates ke mala. How do we get conjugates? We take every element of group, take x inverse ax. So E inverse phi E, phi inverse phi E, psi inverse phi psi, not E and phi also, yes. Then psi square inverse phi psi square. Then phi psi inverse phi phi psi. बीच में तो phi आएगा, x inverse ax. बीच में phi, x inverse psi phi inverse psi phi. Okay, what are these elements? All these 6 will be conjugates. 6 elements are there, so at most 6 conjugates, but there will be some clashes. So there will be only 3 distinct, as we have found from here. The number must be 3 by the above theorem, so very useful. Either you find conjugates, then you can know the number of normalizer, order of normalizer, or you find the normalizer, you know the number of conjugates. It just divide by the order of group by that. So this is going to be phi. What about this? Phi inverse, that is again, so this is phi. So you see there is a repetition. This is phi. So phi is conjugate of phi. So far we have not found any other conjugate. What about this? Psi inverse phi psi. Psi inverse is, let me write psi inverse as it is, and phi psi as, phi psi can be written as psi square phi. Phi inverse, yeah, so psi square phi. So that means I have written phi psi as psi square phi. And then what do I get? This is psi phi. Psi inverse and psi square, so one psi gets cancelled, so this is psi phi. Okay, we have found one conjugate. We should be getting 3, not more than 3. If we get more than 3, we are making some mistake. Right now I am making some mistake if I get more than 3. So this is psi raised to minus 2 and phi psi square. What is phi psi square? Phi psi square is psi phi. So psi raised to minus 2 psi phi. This is what we have used here. This, but this is what? Psi inverse phi. Psi inverse phi is what? Psi inverse phi is psi square phi, and which is again same thing, phi psi. Okay, check this. We know the S3. That is why S3 was important. That's why I said in the first unit itself this is going to come. So see those relations. Now, okay, what is inverse of phi psi? Phi psi is an element of order 2. So order 2 નો element હોય તો એનું inverse શું થાય? X equal to X inverse. X square is identity multiplied by X inverse. So X equal to X inverse. So this is going to be phi psi and then phi અને પાછું phi psi. Right? Now what happens? This is identity. This will give us identity. Phi square is identity. So we have phi and then psi psi is so phi psi square. So which is nothing but phi psi square, which is psi phi. So we have psi phi. Here we have this. And what about last one? Last one is psi phi inverse. Psi phi inverse is again psi phi because it is an element of order 2. So this is psi phi, phi and psi phi. But again, what is identity? This is phi square is identity. So on the left side we have psi square phi. So this is psi square phi. And what is psi square phi? This is phi psi. So how many different people are there? So one is this phi. Phi here is also phi. So phi is of course conjugate of phi. Another is psi phi. Psi phi. Psi phi, yes. And the final, the another one, that is phi psi. Phi psi. So you see each one is repeating twice. That is also another observation which we cannot generalize, but at least we are getting 3. So what is CA? So I can write C of phi. So hence C of phi. C of phi equals to 3 elements: phi, phi psi, and psi phi. So these are the 3 elements. As we expected, we are going to get 3 elements, and it is precisely these 3 elements. Now comes આવું તો 6 elements તો કરો ને, A equal to psi. So take evaluate, compute, or find n psi, which I have written in my notes somewhere. Let me check and write. So n psi is what I am getting is E psi square. I have not written. I'm just writing. Verify this, huh? And so verify, not find. Verify. And similarly, conjugates of psi. एक तो psi तो आवे, psi भूली जाओ तो making mistake. So these are this. So verify this and this. So that is for you to verify. And similarly compute all others. So as an exercise, find NA and CA. So 3 elements, 2 elements I have done, third one is I have done, but I have asked you to verify, so that also you have to do. And remaining 3 elements, psi square, phi psi, and psi phi. So find NA and CA for the remaining A in S3. That is A equals to psi square, phi psi, and psi phi. Right, so this will give you a good practice about this. And as you can see here also, n psi has 3 elements, and C psi has 2 elements. So 6 divided by 3, so that is 2. So if you find C psi, you know there are 3 elements in normalizer of psi. If you find normalizer of psi and you find 3 elements, you know that there are going to be 6 by 3, there is 2 elements which are conjugates of psi. So I stop here, and we'll discuss the same thing in the Google Meet today at afternoon lecture. Okay, just see the video. If you have any difficulty, you can ask. I'm not asking you to see the video before the class, so don't worry about that. It's going parallel. Sometimes I make video before the class, sometimes I make video after the class. But videos will be there in addition to the class. So if you have any difficulty, you can go back video. If you miss any class, if you have any internet connection problem, you can see the video. If you have revision, if you want to do revision, you can see the video. So this is especially for this year I am making this. Okay, so here I stop. Thank you.